Welcome to this deep dive into first principles thinking. Today we're going to explore one of the most powerful mental models in science and problem solving. So what exactly are first principles? In science and philosophy, first principles are the fundamental truths or axioms that cannot be deduced from any other proposition. First principles are the foundational truths that cannot be broken down any further. They are the bedrock upon which all other knowledge is built. Aristotle defined first principles as the first basis from which a thing is known, in other words, the irreducible components of understanding. Think of knowledge as concentric circles. At the very center are first principles, the core truths. Moving outward, we have direct deductions, then complex models built on those deductions, then assumptions we make, and finally, at the outer edge, the biases and heuristics we develop from experience. Now let's discuss a fascinating phenomenon, the expert paradox. How can experts, with all their knowledge and experience, sometimes be outperformed by beginners? Experts develop cognitive schemas which are mental shortcuts based on years of experience. While these shortcuts are usually helpful, they can also become cognitive traps. These mental shortcuts create blind spots. Experts may automatically dismiss solutions that don't fit their established mental models, even if those solutions are actually valid. The expert brain is filled with rigid schemas and patterns, while the beginner brain has open space for new approaches. This is why beginners sometimes see solutions that experts miss. This cognitive bias is formally known as the Einstellung effect. Let me explain what this means. Einstellung is a German word meaning mental set or attitude. It describes how prior knowledge can actually prevent us from finding better solutions. When you know a solution that works, your brain tends to default to that solution automatically. This blocks you from discovering superior alternatives that might exist. Let me give you a classic example from cognitive psychology, the water jug problem. You have 3 jugs. Jug A holds 127 liters, Jug B holds 21 liters, and Jug C holds 3 liters. Your goal is to measure exactly 100 liters. The solution is A minus B minus 2 times C equals 100. That's 127 minus 21 minus 6, which gives you exactly 100 liters. Now suppose you solve several problems using this same formula. Your brain learns this pattern. But watch what happens with a new problem. Now you have Jug A with 23 liters, Jug B with 49 liters, and Jug C with 3 liters. Get exactly 20 liters. Experts who learned the previous formula often use B minus A minus 2C, which is 49 minus 23 minus 6 equals 20. This works, but it's unnecessarily complex. But look at this. A minus C equals 20. That's 23 minus 3 equals 20. This is much simpler. Beginners who haven't learned the complex formula often find this simple solution immediately. This perfectly illustrates the expert trap. Experts became fixated on their learned solution and missed the obvious simpler approach that beginners discovered. Let's look at how first principles thinking revolutionized physics. Consider Newton's laws of motion. Newton's second law, force equals mass times acceleration. This is a first principle in classical mechanics. Before Newton, Aristotelian physics dominated for nearly 2,000 years. Aristotle believed that objects needed continuous force to maintain motion. Newton questioned this assumption. Newton went back to fundamental observations. He asked, what actually happens when I observe moving objects? This first principles approach led him to discover that objects maintain constant velocity unless acted upon by force. By thinking from first principles, Newton realized that an object in motion stays in motion without any force. This contradicted 2 millennia of expert consensus. Let's examine how first principles thinking drives modern innovation, particularly in engineering and technology. Consider the problem of battery costs. For decades, experts said that battery packs would always cost around $600 per kilowatt hour. This was the established assumption. The expert consensus was $600 per kilowatt hour. Everyone in the industry accepted this as fact. But a first principles approach asks, what are batteries actually made of? What are the raw material costs? Batteries contain cobalt, nickel, lithium, aluminum, carbon, and some polymers. When you look at commodity prices for these raw materials on the London Metal Exchange, they total much less than $600. The raw materials cost approximately $80 per kilowatt hour. This is vastly less than the expert assumption of $600. The enormous gap between $80 and $600 represents inefficient manufacturing processes, markups, and the assumption that costs couldn't be reduced. By redesigning the manufacturing process from first principles, considering the actual physics and chemistry involved, modern battery production has achieved costs approaching $100 per kilowatt hour. Let me give you a mathematical framework for understanding the difference between reasoning by analogy and reasoning from first principles. Reasoning by analogy says the new solution approximately equals the old solution plus some small modification. This is incremental thinking. First principles reasoning says the solution is a function of the fundamental principles P1 through Pn. We rebuild from scratch. Now you might ask, when should you use first principles thinking versus relying on expert knowledge? Use first principles when facing truly novel problems, when current solutions are unsatisfactory, or when you want to challenge established assumptions. It's cognitively expensive, so use it strategically. It's important to understand that first principles thinking has a high cognitive cost. Let me explain why. Thinking from first principles requires much more mental energy than using learned heuristics and patterns. Your brain must actively process, rather than rely on automatic responses. The time investment is substantial. You must carefully break down every assumption and rebuild from fundamental truths. This can take hours or days instead of seconds. Heuristic thinking is fast and requires low mental energy. First principles thinking is slow and requires high mental energy. Both have their place in problem solving. Let's examine how first principles thinking led to quantum mechanics, one of the greatest scientific revolutions. By the late 1800s, classical physics had a problem. It couldn't explain blackbody radiation. Experts tried to patch classical theory with various modifications. Max Planck took a first principles approach. He proposed that energy equals h times nu, where energy comes in discrete packets called quanta. This was revolutionary. Planck questioned the fundamental assumption that energy is continuous. By going back to first principles and asking what if energy is quantized, he solved the blackbody problem. Many experts initially resisted quantum theory because it violated established classical mechanics. They were trapped by their expertise in the old paradigm. Interestingly, younger physicists who weren't as deeply invested in classical mechanics embraced quantum theory more readily. They weren't trapped by expert knowledge. Let me give you a practical 5-step framework for applying first principles thinking to any problem. Step 1. Identify and clearly write down all your current assumptions about the problem. Be brutally honest about what you're taking for granted. Step 2. Break down the problem into its most fundamental components. What do we know for certain? What are the basic physics, chemistry, or mathematics involved? Step 3. Create new solutions by reasoning up from these fundamental truths. Don't rely on analogies to existing solutions. Step 4. Test your new solution rigorously against empirical reality. Does it actually work? Can you measure and verify results? Step 5. Iterate and refine based on feedback. First principles thinking is not a one-time exercise, but an ongoing process of refinement. Here's a fascinating historical example: the 4-minute mile barrier. For decades, sports scientists and experts claimed that it was physiologically impossible for a human to run a mile in under 4 minutes. This became accepted wisdom. Roger Bannister questioned this assumption. He asked, what is the actual physiology? What are the fundamental physical limits? He trained based on first principles of human performance. On May 6, 1954, Bannister ran the mile in 3 minutes 59.4 seconds. He broke the so-called impossible barrier. Here's the fascinating part. Within just 3 years, 16 other runners also broke the 4-minute barrier. The limitation was mental, not physical. Expert consensus had created a psychological barrier. Once one person proved it was possible, by ignoring expert assumptions and going back to physiological first principles, others quickly followed. The expert knowledge had actually been holding everyone back. Let's explore the neuroscience behind why experts get trapped by their own knowledge. Every time you use a particular mental pathway or solution, the neural connections for that pathway strengthen. This is called Hebbian learning. Neurons that fire together, wire together. This neurological strengthening creates automatic expert responses, which is usually good for efficiency. But it also creates inflexibility. Your brain literally becomes wired to default to familiar patterns. This is a representation of a well-worn neural pathway. The strong connections make this the automatic default route. Alternative pathways exist, but are much weaker. The solution to the expert trap is maintaining cognitive flexibility. Let me explain how. Deliberately practice considering alternative approaches, even when you have a working solution. This keeps alternative neural pathways active and prevents rigid thinking. Expose yourself to diverse fields and perspectives outside your expertise. This cross-pollination of ideas helps prevent narrow expert thinking and opens new solution spaces. Periodically question your fundamental assumptions, even about things you're certain of. Make it a habit to ask, what if I'm wrong about this basic premise? Let's look at the mathematics of how problem complexity grows and why first principles matter. If problem complexity grows as 2 to the n, where n is the number of variables, then a problem with 10 variables has over 1,000 possible combinations to consider. Expert assumptions reduce the search space dramatically, which is why they're useful. But they may also eliminate the optimal solution from consideration. First principles thinking expands the search space back to its full size. This is more cognitively expensive, but can find solutions that assumption-based reasoning misses entirely. Let's examine a modern case study: SpaceX and rocket reusability. For decades, aerospace experts agreed that orbital rockets must be expendable. The cost and complexity of recovery was assumed to exceed any benefits. First principles thinking asked, why throw away a multi-million-dollar rocket after one use? No other transportation system works this way. By questioning fundamental assumptions and going back to physics first principles, SpaceX designed rockets that could land vertically and be reused. Experts said this was impossible or impractical. The result: launch costs have dropped by more than a factor of 10. First principles thinking disrupted an entire industry by questioning what experts took for granted. Now I need to address an important caveat: the danger of naive first principles thinking. Not all expert knowledge represents bias or error. Much of it is hard-won wisdom that actually reflects deep truths about reality. Beginners using first principles may miss important constraints that experts understand through experience. There's a difference between questioning assumptions and ignoring reality. The key is balance. First learn what experts know and why they believe it. Then thoughtfully question whether those beliefs are fundamental truths or merely convenient assumptions. For example, in medicine, first principles thinking might suggest a treatment, but expert knowledge of human physiology and past clinical failures is crucial. Naive first principles without domain knowledge can be dangerous. Let me share the Feynman Technique, which combines first principles with deep understanding. Step 1. Choose a concept you want to understand. Try to explain it in simple language as if teaching a child. Step 2. When you struggle to explain something simply, you've found a gap in your understanding. This reveals where you're relying on jargon rather than true comprehension. Step 3. Go back to the source material and rebuild your understanding from first principles. Don't just memorize, truly understand the underlying mechanisms. Step 4. Simplify your explanation further and create analogies. If you can't explain it simply, you don't understand it well enough. Let's discuss the broader implications of first principles thinking for learning and innovation. Education systems should focus more on teaching thinking tools like first principles reasoning, rather than just transferring facts and established procedures. True innovation requires the willingness to respectfully challenge authority and question whether the expert consensus represents fundamental truth or historical accident. The beginner's mind, unburdened by expert assumptions, is a strength to be cultivated, not a weakness to be quickly eliminated through conventional training. Let me give you a quantitative framework for understanding the magnitude of the expert trap. If there are n possible solutions and only one is optimal, the probability of finding it by random search is 1 over n. An expert reduces the search space to n assumed solutions based on experience. The probability of finding the optimal solution is now 1 over n assumed, which is higher if the optimal solution is in that reduced space. But here's the critical point. If the optimal solution is not in N assumed, the probability drops to zero. The expert will never find it because they've eliminated it from consideration. Here's a medical example that perfectly illustrates this: the ulcer treatment revolution. For over 100 years, medical experts were certain that stomach ulcers were caused by stress, spicy foods, and excess stomach acid. This was taught in every medical school. Standard treatment involved antacids and lifestyle modifications. Patients were told to reduce stress and avoid spicy foods. In 1982, Barry Marshall and Robin Warren questioned this fundamental assumption. Using first principles and direct observation, they discovered bacteria called Helicobacter pylori in ulcer patients. They proposed that ulcers were actually caused by bacterial infection, not stress. This contradicted a century of expert medical consensus. The medical community rejected this idea for years. Experts couldn't believe they'd been wrong for so long about something so fundamental. Marshall literally drank a culture of H. pylori bacteria to prove his point. He developed gastritis, then cured it with antibiotics, demonstrating the bacterial cause. Today, ulcers are treated with antibiotics, not just antacids. This simple shift in understanding, born from first principles thinking, has saved millions of lives and billions of dollars. Marshall and Warren won the Nobel Prize in Physiology or Medicine in 2005. Their story shows how questioning expert consensus from first principles can revolutionize entire fields. Let me summarize the key takeaways from this lesson on first principles thinking. First principles are the irreducible foundational truths that cannot be broken down further. They are the bedrock of understanding. Experts develop cognitive biases and mental shortcuts from experience. While usually helpful, these can become traps that prevent discovery of better solutions. Beginners can sometimes outperform experts by ignoring flawed assumptions and rebuilding solutions from fundamental principles. First principles thinking requires high cognitive effort and should be used strategically, but it's one of the most powerful tools for innovation and problem solving. The optimal approach balances respect for expert knowledge with a willingness to question fundamental assumptions when evidence or logic suggests they may be flawed. We've seen examples across multiple domains: physics with Newton and quantum mechanics, engineering with batteries and rockets, medicine with ulcers, and cognitive psychology. To avoid the expert trap, cultivate cognitive flexibility, expose yourself to diverse perspectives, and periodically question even your most certain beliefs. Let me leave you with a final thought to ponder. What assumptions are you making right now in your own field or area of study? Which of your beliefs are based on first principles, and which are based on inherited wisdom that might be flawed? I challenge you to take one concept you think you understand well and try to rebuild it from absolute first principles. You might be surprised by what you discover.